We've already discussed the kinetic molecular theory as it applies to gases and liquids. Now we're going to look at how the kinetic molecular theory of solids affects the basic characteristics of the solids. For solids, the kinetic molecular theory tells us that all solids are made up of tiny particles. Those particles are held closely together by strong attractive forces. The solid particles move with an average kinetic energy that is dependent upon the absolute temperature, and because of the strong attraction between the particles, their motion is limited to vibration about a fixed point. And again, these will tell us more about their basic characteristics of a solid, but let's talk about each one individually. All solids are made up of tiny particles, just like we saw for the gases and the liquids, but in this case, the particles may be atoms or molecules or ions. In fact, if there are ions, it is most likely to be a solid, so we can see that most ionic compounds will be solids. They are very rarely liquids, only at very high temperatures, and we don't see ions as gases. Those particles are held closely together by strong attractive forces. This detail actually gives us a lot of differences in the properties of solids that is different from the liquids and gases. In our previous model, we said that gases were not in contact with each other, so they were holding on to themselves. They weren't holding hands with anything else. They were just bouncing around, bouncing off of each other. When we looked at liquids, they were holding hands so that they could move past each other. When we look at solids, I would give an example of them would be like they were hugging each other. So everybody was in this giant group hug, and you'll see how hard it is to move because of that. And that would be more like a strong attractive force. You'll notice that things are closer together and that they're really unable to move. That will describe some of the properties of solids, and why we see them is because they are held together by these strong attractive forces. As with gases and liquids, the solid particles move with an average kinetic energy that is dependent upon the absolute temperature. And all this says is that they will move faster as they get heated because they have more energy. As the temperature increases, they will start to move faster and faster. And as we saw with gases and liquids, those particles will move in straight lines until they bump into something. But think about what happens if you are hugging somebody and everybody around you is in one giant group hug. How far can you move before you bump into somebody? And that explains the last part of the kinetic molecular theory of solids, and that is, because of the strong attractions between the particles, their motion is limited to the vibration about a fixed point. As they start to move, they can't move very far because they're going to bump into another particle. So as soon as they start to move, they just bump into something, so all they can do is vibrate. So that's what we see as a major difference between the solids. They can't slip past each other. For the liquids, they could slip past each other, but they couldn't go far. They couldn't just escape wherever they wanted to. And in the case of gases, they could move around freely. The kinetic molecular theory of solids helps us to describe the basic characteristics of those solids. And those basic characteristics are that solids have a definite shape and volume. Their density varies, but generally they are more dense as a solid than a liquid. They are not compressible, and solids do not flow or diffuse, and solids only expand slightly when heated. We're going to look at each of those individually to see how they compare to the gases and the liquids. Solids have a definite shape and volume. This is because those particles are held closely together, and they're held together tightly. They're very strong bonds, so they can't move around. They don't flow and diffuse, so they're going to stay in the same shape that they originally had. So if I take a sugar cube and I put it in a balloon, it's going to still look like a sugar cube. If I put it inside of a tall glass, it'll still look like a sugar cube. If I put it inside of a brandy snifter, it'll still look like a sugar cube. No matter what container I put it into, it will have the same shape, the same size. The density of solids can vary dramatically, and that depends upon the structure of the way that they're packed together. Sometimes they're packed tightly and very dense, and other times they're packed a little more loosely and less dense. In general, the solid is more dense than the liquid, which is more dense than the gas. So generally we will see the gas on top, then the liquid, and then the solid on the bottom. And I think of it kind of like going to the beach. We'll see the air on the top, and then we'll see the liquid water, and then the solid sand at the bottom. And that's generally true. But there is one major exception to this rule, and that's water. So according to this rule, we should see gaseous water at the top, which is what we do see. Then we should see liquid water and then ice, and ice should be at the bottom of the container. But we don't actually see that. When you have a glass of water, you should see that the ice cubes float at the top rather than sinking to the bottom. And that's because of the way that the particles are held in the liquid. They're very close together, but in the solid, they spread out a little bit. They get a little more comfortable and they move out a little bit. And so they are less dense. In the case of water, the solid is less dense than the liquid. And actually, this is really important for life on Earth, because without that, we would have seen that the ice was at the bottom of the lake, the bottom of the ocean, the bottom of anything, and it would freeze at the bottom first, and then it would never thaw because the sun wouldn't reach it. But because of the way that water's density is, it had the interesting property that the solid was at the top, which left the liquid down below so that the fish and other things could survive even though the top froze over and the lake would be frozen, what seems to be solid at the top, but then there was still a liquid down below, and the sun would beat down and it would melt the stuff at the top. And so we would see this cycle of life continuing because the density of the solid water was less than the density of the liquid water. Again, that is very unusual. Water is a very unusual substance, and it is one of the reasons we have to have water to have had life on Earth. We also know that solids are not compressible. That means if we squeeze on them, they won't shrink in size, they won't compress, get closer together. And that is because those particles are already as close as they can be. They're already in a hug. How much closer can they get, right? So they're already squeezing together. They can't get any closer together, so they stay the same size, even if you squeeze them or try to push them more. I know some people have a little bit of trouble with this concept, so I just want to explain. If you sit on a seat cushion, that does compress, but it's not the solid that's compressing. The solid might be squeezing over and sliding, but what's actually compressing is the gas that's holding it up. When you look at foam, it's a solid, but inside are lots of gas pockets, and those gas pockets are what's being compressed, and it's pushing particles of the solids closer together, but it's not actually compressing the solid. It's only compressing the gas that's inside of the solid. So overall, though, we know that solids do not compress. We also know that solids do not flow and they do not diffuse. If I put a sugar cube on the counter, it'll just sit there. It won't start to spread out. It won't move around. Nothing will happen. If I put a sugar cube and I put on top of it a piece of carbon, nothing's going to happen. They're just going to sit there. It's not going to spread around. And this is caused by the fact that solids can only vibrate. So they can't move around because they're only vibrating. They're stuck together so tightly that they can't move from place to place. So they don't flow and they don't diffuse. And finally, solids do expand slightly when heated. Since solids are commonly used in construction, we can actually see some effects due to this expansion when heated. The first example would be something like cement. When cement is poured, you'll often see that there's a piece of wood or a slit that is cut into the concrete, and that is used to allow for expansion when heating. If the cement is poured on a cold day, then it will expand as it gets heated, and you'll start to see that those will crack because they have nowhere to expand unless you have those little dividers in there. Those dividers are made of wood in general, but their main purpose is to allow a space for expansion of the cement. They may have gas particles inside of the wood, and that may be allowing it to compress. If you live in an older area, you won't see those wood anymore, but you'll see the lines in the cement that allow for the expansion. If you don't allow for that expansion, you'll start to see that you'll get lifting and that sort of thing in the cement, not due to roots of a tree, but due to the expansion of the cement. We also see this in bridges. When you look down at a bridge, sometimes you'll see these metal fingers. Those are to allow for expansion and contraction of the bridge, and the bridge won't have a big gap in it as long as we have those fingers there to allow them to kind of crisscross. And that again allows for expansion of the solids. The expansion of the solids is similar to what we would see for the liquids. Again, there's not a huge amount for liquids, and it's not really, really big for solids, but it does have an impact on our construction. So that's why we mention it. But again, with gases, those will expand greatly when they're heated. So liquids and solids are more similar. The gases are very different in this characteristic. There are two general types of solids that can be found. The first type is crystalline, the second is amorphous. The crystalline solids have some sort of repeating pattern so that they look like crystals. They tend to sparkle, characteristics that we normally associate with crystals. The amorphous solids have no repeating pattern. They just kind of are a clump of things. They're more gelatinous or just kind of piled up. And so the amorphous solids don't have a repeating pattern, whereas the crystalline solids do. And here are a few examples. These ones all show some crystalline solids, and down here we can see some amorphous solids where they're just kind of not defined shapes. Overall, we can see how the kinetic molecular theory of solids affects the basic characteristics of solids, and we also know that there are two general types of solids, the crystalline and the amorphous.